Hey guys, in this video I'll talk about an application of differentiation called optimization. So this is when you're given some function that you want to optimize. So you want to either find the maximum or minimum value. And you're given another function that you're restricted to. So you want to optimize one value and you're restricted to another. So you want to start off by converting the words you're given into equations. So you're usually given a pretty lengthy word problem that describes a real-world situation that you want to optimize. And so you usually convert it into two equations. One would represent the function that you want to optimize, and one would represent the function that you're limited to, the restrictions that you're given. Once you do this, you want to convert those two equations into one equation with one variable. And you can do this by substituting one of the variables. Once you make this one equation, you want to find the critical points of the function you created. So a critical point is when a function's derivative is equal to 0. And this is important since this is where the function changes direction. So it's either a local minimum or a maximum. And this is because a positive derivative means the function's increasing, a negative derivative means the function's decreasing. So a critical point where the function's derivative is 0 is when it's either going from increasing to decreasing, which would mean it was a local maximum, or decreasing to increasing, meaning it would be a local minimum. And once you find critical points, there could be one or there could be many, you want to test the point and check if it's a minimum or maximum. And you would do this just by plugging it back in the function and comparing the values that you get. So now let's take a look at an example to see how we can apply this. So let's say we have 20 feet of fencing, and we want to make a rectangular garden that's surrounded by a fence on all 4 sides. And you want to find the dimensions of the garden that we make that has the most area possible. So in this example, area is what we're trying to optimize. You want to find the maximum area, and we're restricted by the 20 feet of fencing we're given. So we're restricted by the perimeter. So we can draw this diagram just so we can visualize this better. So we want 20 feet around, and we want the maximum area that we can do with 20 feet. So we'll start off by writing our two equations, converting these words into equations. We know that the perimeter is given by 2x plus 2y, and it's also 20, which is given in our problem. So this is our restriction. This is what we're restricted to. And the value that we want to optimize is area. We can write our function a equals xy, which is the area that we're trying to optimize. So now we want to convert these two equations into one equation with one variable. So let's first solve for y using the perimeter equation, and we get that y equals 10 minus x. So now we can just plug this value for y into the area equation, and we get the area is equal to negative x squared plus 10x. So this is the one equation, the one function that we made, and now we want to optimize. So we find the critical values of this function by taking the derivative first. So using the power rule, we can see that the derivative of a is negative 2x plus 10, which means our critical point where the derivative is 0 is 5. So in this case, we only have one critical point because the only way the derivative can be 0 is when x equals 5. And let's just check this by plotting 5 and seeing what the derivative is before and after. So when x is less than 5, the derivative is positive. And when x is greater than 5, the derivative is negative by plugging it into the derivative equation. So you can see the function would increase until it gets to 5 and then decrease, which makes it clear that 5 is the maximum value of the area function. So now we know that x must be 5 in order to have the most area given 20 feet of fencing. And now we just plug in x into the perimeter equation and solve for y, and we find that y is also 5. So we just found out using optimization and derivatives that using 20 feet of fencing, the dimensions of a rectangular garden with the most area is 5 by 5 feet.